This lecture is Introduction to Linked List, Part 1, Memory Management. In this lesson, we will introduce you to a linked list data structure. This lesson is in two parts. Part 1 will explain memory allocation within programs and how arrays are incorporated into computers' memory. Part 2 will continue with linked lists both logically and how memory is allocated for this data structure. In a previous lesson, we tried to implement a dynamic list using arrays and had some issues there. It was not efficient in terms of computer memory consumption. When we use arrays, we have some limitations. To be able to understand linked list well, we need to understand these limitations. So I'm going to tell you a simple story to help you understand this. Let's say this is a computer's memory and each section is 1 byte of memory. Now, as we know, each byte of memory has an address. We're showing only a section of memory. Let's say the memory address increases from left to right. So let's say this first byte is at address 200. And the next one is at address 201. And so on. This is just a logical way of looking at computers' memory. So, coming back to our story, memory is a crucial resource of all applications keep asking for it. So, Mr. Computer has given this job of managing memory to one of his coworkers, and he calls the memory manager. Now this guy keeps track of what part of memory is free and what part of memory is allocated, and anyone who needs memory to store something needs to talk to this guy. This is Albert. He's our programmer and he's building an application and he needs to store some data in memory, so he needs to talk to the memory manager. He can talk to the memory manager in a high-level language like C. First, he wants to store an integer in memory. He communicates this to the memory manager by declaring an integer variable. Something like this. The memory manager sees this declaration and says, "Okay, you need to store an integer variable, so I will give you 4 bytes of memory," because an integer variable is stored in 4 bytes in a particular architecture. And let's just say that in this architecture, it is stored in 4 bytes. So the memory manager looks for 4 bytes of free space in memory and assigns for variable x. Address for the block of memory is at the first byte of the block of memory. So let's say that this byte is at address 217. So variable x is at address 217. So the memory manager kind of communicates it back to Albert that, hey, I've assigned address 217 for your variable x, and you can store whatever you want there. And Albert can fill in any data into this variable. Now, Albert needs to store a list of integers, and he thinks that the maximum number of integers in the list will be 4. So he asks the memory manager for an array of integers of size 4 named A. Now arrays are stored in memory as one contiguous block of memory. This means they're all together. So the memory manager is like, oh, I need to look for a block of memory with the size of 16 bytes for this variable, this array A. So the memory manager assigns this block starting at address 201 and ending at address 216 for this variable A, an array of 4 numbers. Because array is stored as one contiguous block of memory, and the memory manager conveys this starting address of this block. Whenever Albert tries to access any of the elements in the array, let's say he tries to write some value at the 4th element in the array, which he accesses as A3, Albert's application knows to write this particular value because it knows the base address or starting address of block A, array A, and from the base address, using the index, which is 3 here, calculates the address of A3 and knows that it is at address 213. So to access any of the elements in the array, the application takes constant time. And this is one of the awesome things about arrays, in that irrespective of the size of the array, the application can access any of the elements in the array in constant time. Now let's say Albert uses his 4 integers to store his list. So I'll just fill in some values here. Now Albert at some point feels, okay, I want to have one more element in my list. Now he has declared an array of size 4 and he wants to add a 5th element in the array. So he asks the memory manager, hey, I want to extend my array A. Is it possible to do so? I want to extend the same block. And the memory manager is like, when I allocate memory for an array, I do not expect that you will ask for an extension. So I use whatever memory is available adjacent to the block of the other variables. So in some cases, I may extend the same block, but in this case, I have an element of variable x adjacent to your block, so I cannot give you an extension. So Albert is like, so what options do I have? The memory manager says, you can tell me your new size and I can create a new block at a new address, and you will have to copy all of the elements from the previous block to the new block. So Albert says, okay, let's do it. And the memory manager is like, you still need to give me the size of the new block. Albert thinks at this time he'll use a really large size for his new array or new block so that it does not fill up. This new block starting at 224 is allocated. Albert asked the memory manager to free the memory from the previous block, and at some cost he has to copy all of the elements from the previous block into the new block, and now he can add one more element to his list. And he has kept his array large this time in case he needs to add more numbers in a list. The only option Albert has is to create A as an entirely new block. And Albert is still feeling bad because if this list is too small, he is not using some part of the array, and so memory is getting wasted. And again, if the list grows too much, then he will have to create a new block and copy all of the elements from the previous block to the new one. Albert is desperately seeking a solution to this problem, and the solution to this problem is a data structure called linked list. And in part 2, we will analyze this problem and look at linked list in a logical manner. Until next time, see you.